We're going to talk about moles now, which is probably the single most important thing in chemistry. So pay attention. Let's talk about a fancy word, stoichiometry. Okay? What the heck is stoichiometry? Well, stoichiometry is probably the single most important topic in chemistry because it's really going to show up in lots and lots and lots of different places, here and also in subsequent sections and modules. So the word stoichiometry really refers to the amounts of a species or a substance. And because it has to do with amounts, we sometimes call it the mathematics of chemistry. So let me give you some definitions to show you how these equations in mathematics kind of work out. Okay? First, we're going to talk about a molar mass, or molecular weight. And the molar mass is really just the sum of all the different atomic masses or atomic weights for all of the atoms in a certain molecule. Okay? There's also something called a formula mass, or formula weight, which is kind of found the same way. We just have to add up all of the masses for all the ions in the formula unit. So whether we're talking about molar masses or we're talking about formula masses, either way, we still have to use the periodic table to solve these problems. So what I'm going to do now is show you a high-quality image of the periodic table so you can see how to work this out. Okay, so here's our friend, the periodic table. And let's say that you wanted to figure out the molar mass or molecular weight for water, H2O. Well, first thing I do is I look up hydrogen, and I find it right there. And this bottom number represents the atomic weight, 1.008. I'm going to round this off to about 1. So I'm going to say 2 times 1 because I have 2 of them, and each one has a mass of about 1 gram per mole. And then I'm going to look up oxygen, which has a molar mass of about 16 right there. So if I add this up, I get about 18 grams per mole. Now, if I do this for something like salt, NaCl, I have to do it the same way, except I don't call it a molecular mass, I call it a formula mass, but it's the same idea. I'm going to look up sodium and look up chlorine and add them up. So here's sodium, about 23. And here's chlorine, 35.45. So if I add these up, I get about 58.45 grams per mole. Okay, and so this is how I can use the periodic table to get either molar masses or formula masses, depending on whether the substances are covalent or ionic. So now let me show you how you can use the periodic table to figure out what's happening in an actual chemical reaction. Okay, a very, very important interpretation of this is that when you have a chemical reaction and you balance this chemical reaction, the coefficients have to do with the ratios of the reactants and the products in a chemical reaction. This ratio is present only in terms of molecules, but not masses. Okay, and so let me give you an example. Let's say you were looking at something like methane being combusted or burned in the presence of oxygen to make carbon dioxide and water. Okay, so if I balance this, I need a 2 here for the hydrogens, and now I have 2 O's, and 2 O's is 4. I need a 2 over there. Okay, so these numbers, the 1, the 2, the 1, and the 2, tell me that I can take one molecule of methane and combine it with 2 molecules of oxygen to make 1 molecule of carbon dioxide and 2 molecules of water. Or I could take 1 mole of methane and combine it with 2 moles of oxygen to make 1 mole of CO2 and 2 moles of H2O. But what is wrong, what I cannot say, bad, don't do this, is in terms of grams or masses, right? It's incorrect to say 1 gram of methane and 2 grams of oxygen combined to give me 1 gram of carbon dioxide and 2 grams of water. Okay, these coefficients are giving me ratios in terms of moles or molecules, but not masses. So let me give you an example. Let's say that you're interested in producing nitric acid. And so in the production of nitric acid, we're going to take nitrogen dioxide and combine it with water. And at the same time, also make nitrogen monoxide. Okay, so the question is, How many grams of nitric acid can I make given about 100 grams of nitrogen dioxide that react initially? Okay, so let me show you how to solve this problem. First step, try to write down the chemical reaction and balance it. Okay, and so we know that we're starting with NO2, nitrogen dioxide, and water, H2O, to make nitric acid, HNO3, and nitrogen monoxide, NO. Okay, so I have two reactants and two products. Now I balance this. I can start anywhere I want. Nitrogen shows up in three spots. Oxygen shows up in 1, 2, 3, 4 spots. Hydrogen only shows up in 2 spots. So let me do the hydrogens first. So to balance the hydrogens, I need a 2 in front of the HNO3. That balances that. Then I have the nitrogens. So if I put a 2 there, that gives me 2 N's, and 1 more is 3. So I need a 3 over here. So that balances those. And now I just have the oxygen remaining. So I have 3 times 2 is 6 O's over here. 1 more is 7. 7 O's on this side. Instead I have 2 times 3 is 6, and 1 more is 7. Okay. Oxygen is balanced as well. Everything is good. Now let's figure out the actual amounts. Okay, and so I'm saying this kind of jokingly, but also kind of seriously. If you're not sure what to do with any of these questions, find number of moles. That usually gives you a pretty good starting point for what to do next. Okay, so since I know the mass of the NO2, I can convert that into the number of moles of NO2. So the way I'm going to do that is by using the periodic table. I take the mass of NO2 and I divide it by the molar mass to get the number of moles. So I go to the periodic table, I look up nitrogen, which has a mass of about 14 grams per mole. Oxygen is about 16 grams per mole. So if I have NO2, that's 14 plus 2 times 16, it's about 46 grams per mole. And you can see I did it here a little bit more accurately, 46.006. So if I divide the 100 grams by the 46 grams per mole, I get about 2.174 moles of NO2. So that's the number of moles of nitrogen dioxide that we're starting with. So now we're going to use stoichiometry to figure out the number of moles of product. Okay, and so here's where the balanced chemical reaction comes in handy. Just going to flip back for a second. Okay, I'm comparing the amount of NO2, the reactant, to the amount of HNO3, the product. And I notice that the ratio here is 3 to 2. That means that the number of moles have to be in that same ratio, 3 to 2. So that's this ratio that I set up here. Number of moles of NO2 to number of moles of HNO3 are 3 to 2. Since I actually have 2.174 moles of NO2, I can say that I have X moles of HNO3 and solve for X. So the way to do that is just cross multiply. So I have 3X is equal to 2 times 2.174. If I solve this for X, X is about 1.449 moles. That means that I can hope to make about 1.449 moles of nitric acid. Okay? Unfortunately, this is not the end of the problem. Okay? You have to read the question very carefully. The question didn't ask me what is the number of moles of HNO3 that I can produce. The question was, what is the mass of HNO3 that I can produce? So to convert between moles and mass, I have to use the same equation I had before, but in reverse. Okay, instead of finding the number of moles from the mass, I'm going to find the mass from the number of moles. Okay, so I know that number of moles is 1.449. And then I go back to the periodic table and I calculate the molar mass of HNO3. So I know that hydrogen is about 1 gram per mole, nitrogen is about 14 grams per mole, and oxygen is about 16 grams per mole. So if I add all this up, I get about 63 grams per mole. So if I multiply the molar mass of nitric acid, which is 63.013 grams per mole, multiply by the number of moles, 1.449 moles, I get 91.31 grams of nitric acid. That means that if I start with 100 grams of NO2, I can hope, under the best of circumstances, to make 91.31 grams of my product, HNO3.